guys, and welcome to another calculus video. In this video, we're taking on this absolutely crazy integral that you can see right here, suggested by someone in the Cambridge integration server. This one is absolutely crazy. We're going to do some awesome contour integration, and I've already seen an actually completely different solution to this problem, which makes me really excited because the fact that there's two different contour integration solutions to one awesome problem is just absolutely cool. So let's go ahead and jump right into it. So first of all, our integral is sine of x over 2 over x times cosine sine of x minus 2 sine of x sine of x, all multiplied by e to the cosine of x over 5 sine squared of x plus cosine squared of x dx. So in order to take on this awesome integral, obviously we're going to have to do a little bit of simplification. And we're going to start with these two terms in the top here. What's the relationship between cosine sine of x and 2 sine sine of x? So right here, we notice that here's our, we're trying to simplify this, right? We notice that if we take the real part of e to the ix, we're going to add e to the cosine x times cosine sine of x. And if we want to get something with sine of x, we're going to have to multiply this by an imaginary number. So it turns out if we multiply by I times sine of x, we take the real part of I sine of x times e to the ix. It's going to selectively take out that term with sine of x out of the e to the ix, and we're going to get negative e to the cosine x times sine of x, which is pretty similar to what we have here. So now if we instead take the real part of 1 plus 2i sine of x, we get 1 plus 2i sine of x times e to the ix, and finally, when we take the real part, we get e to the cosine of x times cosine sine of x minus 2 sine of x times sine of x, which is exactly what we had at the beginning. We're also going to use the fact that sine squared of x plus cosine squared of x equals 1 in order to simplify the denominator here. So we get 1 plus 4 sine squared of x, and we can replace the numerator with 1 plus 2i sine of x times e to the ix, and bring this real part operator outside. Now notice we have a 1 plus 2i sine x on the top, and in the bottom we have 1 plus 4 sine squared of x. And we can factor this as 1 minus 2i sine x and 1 plus 2i sine x. We'll cancel the 1 plus 2i sine x on the top and bottom. And now we have the real part of the integral from 0 to infinity of sine of x over 2 over x times e to the ix over 1 minus 2i sine of x. And I should have done this in the last step, but we can split this to 1/2 times the integral from negative infinity to infinity of the same integrand, because the real part of e to the ix over 1 minus 2i sine x is even. You can see this from the beginning. This is clearly an even function right here, and so it remains even after we do this real part bit. So we were going to make this a real part of 1/2 the integral from negative infinity to infinity of sine of x over 2 over x times e to the ix over 1 minus 2i sine x. Now we're going to go ahead and replace everywhere we see sine x with e to the ix minus e to the negative ix all over 2i. And in this case, this 2i just sort of cancels with this 2i. In this case, we're going to bring it out as a 1 over 2i. So now we have a bunch, sort of two separate, a lot of different functions here. But it turns out that all of these functions actually work quite nicely in a nice classic contour integral. So we're going to be calculating the contour integral over a closed contour C of f of z dz. And in this case, f of z is going to be 1 over 4i times e to the iz over 2 minus e to the negative iz over 2 all over z times e to the iz over 1 minus e to the iz plus e to the negative iz. Quite a mouthful, but we're just going to sort of break this up bit by bit, and it turns out there's actually not very many cases we have to deal with where this function won't be analytic. So this is the contour we're going to be using. It's a little bit exaggerated, but it's essentially just our standard semicircular contour. So we're going to go from negative infinity to infinity on the positive on the real axis, and actually I will go ahead and put in arrows here because I just realized I forgot to do that. So go ahead and add those in. And we also are going to go back on a large semicircle on this curve gamma. Now notice I've colored in all these poles right here, which are the red x's, and we'll calculate exactly where those poles are and why they look like this in a moment. And then I've marked this yellow, the origin here, because it looks like we have a pole at the origin, but actually that this is a removable singularity because of this sine of x over 2 on the top, so we don't have to worry about this at all, and we can just treat it as analytic right there. So first of all, we're going to show that this gamma integral goes to 0. So we're going to do this by setting everything to the absolute value, and this is where it gets a little bit fishy, but essentially what we're going to do is set z equal to r e to the I theta. And then for every single part of this function, we're going to figure out what it's asymptotically approaching as r goes to infinity. So in the case of sine z over 2, it becomes e to the r over 2 times sine theta. 1 over z is going to become 1 over r. E to the iz is going to become e to the negative r sine theta, which is going to be essentially 1. And 1 over 1 minus e to the iz plus e to the negative iz equals e to the negative r sine theta. And the way I calculated these is I figured out that essentially as r goes to infinity, the only thing that's going to dominate is whatever becomes very, very large as r grows large, and in that case this is usually the r sine theta terms when we have e to the iz. So that's what we used here in order to actually determine what these are asymptotically approaching. So now, again, this is not an exact substitution here, but essentially we can argue that these will be differing only by a finite factor, so that then we can show that as r goes to infinity, if the product of these functions goes to 0, the integral will also go to 0 because it differs again only by a finite factor. So we can do that right here. And when we multiply everything out, we'll end up with the integral from 0 to pi of e to the negative r over 2 sine theta, or which is the same thing as 2 times the integral from 0 to pi over 2 of e to the negative r over 2 sine theta. Now, between theta equals 0 and theta equals pi over 2, sine theta is greater than 2 over pi theta, so we can go ahead and substitute that in. And then solving this integral just gives us 0 as r goes to infinity, which means that our original integral was also 0. And so that gamma integral goes to 0, which means that we can just evaluate the residues and they'll give us the value of our integral. So, therefore, our contour integral over f of z dz equals the integral from negative infinity to infinity of f of x dx. Now, after we calculate that integral, we do need to take the real part. However, I will go ahead and tell you that the imaginary part is 0, so I think I might leave that out in the rest of the video. And this is also going to be equal to 2 pi I times the sum of the residues of f of z in that upper semicircle. So the poles in this case are only going to occur when the denominator equals 0, because that's the only thing that we can have that can act non-analytically. And so that's going to be 1 minus e to the iz plus e to the negative iz equals 0. We'll let e to the iz equal w, and this yields the quadratic equation w squared minus w minus 1 equals 0. And this is famously the golden ratio phi. So phi equals 1 plus square root 5 over 2, and we get two zeros here. W equals phi and w equals negative 1 over phi. In the case that e to the iz equals phi, we get that z is going to equal negative I times ln phi plus 2 pi k. And in this case, we have a negative imaginary part, which means that it's going to be in the lower half plane. So I'll go ahead and show you those poles on our little graph here. Those negative half plane poles are these ones right here. They lie just under our integral. And notice that there's one on the line imaginary part of z equals 0. Meanwhile, up here there isn't, and we'll see why in a moment. And so we don't actually have to worry about any of these poles because they lie outside our range of integration. So then, in the other case, where e to the iz equals negative 1 over phi, we get z equals I ln phi plus pi plus 2 pi k, and we'll call this zk. And now we're in the upper half plane, so they will be contained by our integral, and now they don't exactly pass through this line where the real part equals 0 like these ones did, because we're calculating e to the iz equals negative 1 over phi, and so the argument is actually shifted over by a little bit, so it doesn't actually pass through the center line. However, that's not of much concern to us. We can still just go ahead and directly calculate the sum of the residues. So we're going to go ahead and do that. So from here, we know that I is the real part of the integral from negative infinity to infinity of f of z dz, which is the real part of the sum of the residues, which is the sum from negative infinity to infinity of the residues of f of z at zk. And this sum from negative infinity to infinity is a sum over k. So when z equals zk, w equals negative 1 over phi, and this means that e to the iz is just going to be e to the negative 1 over phi. That's one. We have sort of 4 functions to deal with here, so we're going to go through them one by one. In order to calculate sine z over 2, or e to the iz over 2 minus e to the negative iz over 2, rather, we can just go ahead and plug in our definition for zk, and we get that e to the I z over 2 equals 1 over square root phi times 1 times negative 1 to the k, or times I times negative 1 to the k, and e to the negative 1 over z, or negative I z over 2 gives us negative I times square root phi times negative 1 to the k. Then we're going to have a first order pole, so this means that we can go ahead and plug in the definition for finding the residue of a first order pole. So we take the limit as z goes to zk of z minus zk over 1 minus e to the iz plus e to the negative iz. So notice I'm only combining it with the part that actually has the pole in it, because the rest of the functions will just be constant in that region, so we can just factor them out of the limit, so we only have to deal with this limit. We'll use L'Hospital's rule, and we get the limit as z goes to zk of I over e to the iz plus e to the negative iz, which is equal to negative I over 2 phi minus 1, which is equal to negative I over root 5. And to get this 2 phi minus 1, I just did some manipulations with the golden ratio, using the fact that phi squared equals phi plus 1, and phi minus 1 equals 1 over phi. Finally, we can go ahead and plug everything in. So we get the real part of 1 over 4i, this was just a constant multiple, negative I over root 5, this comes from the residue part directly, times e to the negative 1 over phi, this was e to the iz, times I root phi plus 1 over root phi, this came from e to the iz over 2 minus e to the negative iz over 2, times 2 pi I, that's just from 2 pi I sum of residues. Then the sum from negative infinity to infinity of negative 1 to the k, this also came from e to the 1 over z, e to the iz over 2 minus e to the negative iz over 2, that's what the negative 1 over k comes from, over I ln phi plus 2k plus 1 pi. And this I ln phi plus 2k plus 1 phi, or pi, is just, that's just z, when z equals zk, and that's just because we had that z in the denominator here in our original function, which is all the way up here. From this z in the bottom, that's where that nasty term comes from. So now all we have to do is sort of multiply all the constants and then evaluate that last summation, and we can finally get the actual value of our integral. So I multiplied all the constants together, and then in order to evaluate this summation right here, we're going to divide by 2 pi on the inside here, and we're going to multiply this all out. So essentially, we're going to get the sum from negative infinity to infinity of negative 1 to the k over k plus 1 half plus I ln phi over 2 pi. Now, the sum from negative infinity to infinity of negative 1 to the n over x plus n equals pi cosecant pi x. So in this case, we have this exact situation, and x just equals 1 half plus I ln phi over 2 pi. So we go ahead and plug this in, and we get pi cosecant pi over 2 plus I ln phi over 2. Now cosecant of pi plus x is the same as secant of x, so we get pi times secant of I ln phi over 2, which is pi ln hyperbolic secant of ln phi over 2, which is 2 pi over e to the ln phi over 2 plus e to the negative ln phi over 2, which equals 2 pi over root phi plus 1 over root phi. And now you see how this is all coming together. We get I equals the real part. Again, this real part doesn't really matter since this is all real anyway, of pi times e to the negative 1 over phi over 2 root 5 times root phi plus 1 over root phi times 1 over 2 pi times 2 pi over root phi plus 1 over root phi. So all of these last parts cancel, and we get our final answer, which is pi e to the negative 1 over phi over 2 root 5, which is the same as pi times e to the 1 minus phi over 2 root 5. What an absolutely awesome integral with an infinite number of residues that we had to factor in. That just happened to be a very, very nice summation. I hope you guys enjoyed this awesome video and this awesome integral. Please let me know if you have any problems you'd like to suggest for future videos. Thanks so much for watching, and I'll see you next time. Bye!